Okay, بسم الله الرحمن الرحيم والصلاة والسلام على أشرف المرسلين سيدنا محمد وعلى آله وصحبه أجمعين. السلام عليكم everyone. Last lecture of the course officially. Okay, so this is the last recorded lecture. We still have two more, as I mentioned. So Tuesday, inshallah, will be an open discussion. I'll stop talking. You'll start talking. So any feedback you have on the course will be greatly appreciated. Yeah, we're gonna have inshallah some interactive form. We're gonna be having the feedback live, so it's not like this boring stuff that you do on the system. Okay, where you just answer a question. Okay, this will be more interactive. So if you have anything that you experience throughout the course, please deliver it next lecture, inshallah. The last lecture will be your presentation. So again, you will be doing all the talking. I'll be doing the listening and laughing. Okay, hopefully just the listening. Okay, but that's it. So hopefully you'll enjoy the course. Today's lecture is on floating base manipulators. If you go back to the first lecture, I promised this would be a whole topic. Okay. It's not trivial. You saw how much we covered in the course, so that was hard to do. There's so much to be discussed in this topic. Or this is actually the start of another course. Okay, so you're going to see how much we didn't cover. You're going to see how much we're still, even though this course, I'm pretty sure you experience it's heavy, maybe heavier than other courses that you have. It's full with material. Some people suggest it to be split into two courses. You're going to see that actually we're still missing a lot. So if I had two courses, I would fill it with more stuff, not divide the first one. But anyhow, so let's start with an overview of floating base manipulators. This is the video stuff. So hopefully there will be okay. So floating base manipulators are usually the interesting stuff. Most of you chose in your projects some type of floating base manipulators. Humanoids are one of them. So a humanoid is a floating base. You can think of the base that's floating as maybe like the torso of the robot, and it has multiple arms that are attached to it, multiple manipulators. One of them is the right hand. The video is so slow. Sorry for that. So the right hand is one manipulator. The left hand is another manipulator. The right leg is a manipulator, and the left leg is a manipulator. So this is an example of a multiple branch floating base manipulator. This is very difficult also because it has contact on the ground. It's the body is not actuated at all. It's just that it's moving by the reaction forces from the ground. Okay, so it also includes contact forces, which is something we didn't discuss at all. Another example, which was the quadrupeds. So quadrupeds with robot arms is another example of a floating base manipulator. Okay, so this video is better. So again, this is the same as the humanoid. So again, it moves on four legs. This is the floating base. It has 1, 2, 3, 4, 5 manipulators onto it. It uses the 4 that are on the ground to move. It uses the 1 on the top to interact with the environment. So then another example of a floating base manipulator. So underwater. So this is an underwater manipulator. So this is not fixed to anything. It's just floating with water. Modeling the water and modeling the fluid is something very complicated because you need to know how the water will behave so that you can design the motions. This is something very complicated. We never talked about anything about modeling the environment. We didn't talk about modeling modeling the contact. So how when I press on the floor, what happens? So this requires some modeling out of the scope. How do we model more water or air or the fluid dynamics? Completely out of the scope of this course. Another example is the drones. Okay, my favorite topic. So the base is floating in the air, and it uses propellers to push on the air, and then the air pushes back. This is how it locomotes. This is how it moves in the air. And then the one emerging field of aerial robotics is this serial linkages, which are manipulator. And then you have this is the base, and this is 1, 2, and 3, 4 manipulators on top of it. So this is also an example of a floating base manipulator. And the last one is space robotics. And space robotics there has a lot of application. This is a very nice video from DLR. So DLR is the German space center. So here they're doing gravity compensation. So they're trying to simulate that this is a facility on ground, and they're trying to simulate whatever would happen, whatever effects that this robot would experience in space, and in space there's no gravity. So they put this robot arm on a base that's actually compensating the gravity. Okay, so when we model, we have the gravity effects, but when they're trying to do this facility, they put it on another robot base so that it cancels out the gravity. And how does it do that? It does it by impedance control. So it's designing the base of the other robot. So this is one robot on another robot. The other robot has impedance control so that it's simulating completely the absence of gravity. And now they're interested only in the top robot, trying to simulate something that it will be doing in space. For example, here capturing this satellite or doing something there. So the bottom line is that floating maze manipulator is not something in the books. Okay, it's really very practical, but it's very complicated. Okay, so what we've been doing is here, and floating maze manipulators go all the way in this direction. Okay, the more linkage that you have, it becomes complicated. When you start talking about contacts, this is also complicated. So legged robots are not that easy. When you have wheels, okay, believe it or not, sometimes wheels are now considered to be harder than legs and locomotion. So they are really complicated because they both actually have something called non-holonomic constraints, and this is something very complicated. So the fixed base, when we have multiple degrees of freedom, but all of them are typically actuated. So we have a fully actuated system. But usually when we have a floating base, the base is unactuated, or sometimes, for example, like a humanoid, the base is moving. We can control it to go from one place to the other. But actually we're indirectly actuating it through the contacts with the ground. So this is leading to, we have an underactuated system. So we have underactuated with multiple links and contacts on the ground. It's very complicated. Sorry. When we have a fixed base manipulator, the base is stationary. The dynamics are usually local only to the manipulator. However, when we have a floating base, the base gets affected by the arms. So if you have just a floating base and the arms start to move, you're going to find that the base is moving, and vice versa. If you have a robot arm and then the base starts to move, it will also affect the dynamics. So we have there are tightly coupled dynamics. And also the base might have holonomic or non-holonomic constraints, depending on whether it has wheels on the ground, whether it's moving with legs and so on. Stability, when we have a fixed base, we never talk about stability, only stability of the equilibrium point we want to go to. But when we have a floating base, the first thing we think about is that this robot doesn't fall on the ground. So we just have, before doing anything else, we just want it to be stable. We want it to stand alone without with actuation, of course, but not to fall down. So this is also something it's very important that we need to take into account, a very important issue. The fixed base, we have external reaction forces that are transferred to the environment. So each joint had an actuator. So when we actuate all of these actuators, when we supply some power to them, we start moving the end effector and we do something. However, when we have floating base, we have a weird combination of internal forces and torques. And we cannot just rely on the ground and the reactions. We also need to take into account the conservation of momentum. Conservation of momentum is a law of physics. So we need to manage it by control to make sure that we're not violating this, so on. And we try to do controllers that take this into account. Yeah, okay. And also when we have fixed base manipulators, we looked at two types of controller, one which is in the joint space, when we're designing the torques directly by measuring the theta and the theta dots and theta double dot if needed. Or we can have a task space control when we look at the end effector and also feedback its pose, its angular, its velocity, and the velocity rate. However, when we're talking about a floating base, it's highly nonlinear. We need to talk about whole body control. Whole body control is a type of optimization. We try to design an optimization controller to take into account the constraints that the system has, and we try to prioritize, because usually we have a lot more degrees of freedom than that's needed. So we have an over-actuated, we have multiple degrees of freedom, usually actuating the same directions. So we need to prioritize. We need to do some ranking of what is the top priority. So top priority for any floating base manipulator is not to fall down, and afterwards you can have more hierarchy of the tasks. We also need to take into account the constraints. This is also very complicated. So bottom line is difficult. Okay, so that's the bottom line of floating base manipulators. To do it really properly, to do it in a geometric way is even way harder. What I'm gonna only doing in this lecture is just to show you something like a silver shining in the clouds, which is it's not silver shining, silver lining, right? Yeah, silver lining. Okay, sorry. Yeah, silver lining in the clouds, which is that when we do the geometric way of the dynamics for a fixed base manipulator, when we extend it to the floating base, it's almost very easy. Okay, I would say trivial, but it's not that trivial. But again, it's really very easy. With the same set of tools that we learned, you're going to be surprised that we're going to be able to design, okay, or at least derive the equations of motion that govern floating base manipulators. This is only given that we do it in the geometric way that we learn. So this is the good news about it. We're not going to be talking about any control. Okay, this is open for research. So this is really what people are doing research at. This is the level of the research. Okay, in robotics now, how do we model? How do we actually even the modeling itself? You can do research in just modeling floating base manipulators because there are many ways that we can rewrite the equations depending on what are the important variables that you want to describe. So this is a recap of the fixed base dynamics. So everything here is, you should know it. I'm just going to be writing it slightly different so that we can easily extend it to the floating base case. So everything here you should know about. So the structure when we're talking about a fixed base manipulator. So this is fixed base stuff first. So the structure of a fixed base manipulator is that we have n rigid bodies. And we have a combination of revolute joints and prismatic joints. Okay, but in the end, we're going to be assuming that all of the joints are actuated. So we have NP, NR revolute joints, and NP. Sorry, this should be prismatic joints. So NP prismatic joints and NR revolute joints. NR and NP, that some of them should be N. So in the end, we're actuating all of the bodies that are attached that make up this fixed base manipulator. We attach one frame, a body fixed frame, when we call it frame I, to the ith body, and we have bodies from 1 to n. The frame 0, we attach it to the base, and we consider that this base was usually fixed. So this is the fixed base, and the the 0 frame is the S frame, is the stationary frame. From now on, we're going to be calling this the S frame. Okay, so the stationary frame, which is what we usually call the 0 frame, we're going to be calling it the S frame. The configuration space, we have two types of configuration space. First of all, we have n rigid bodies. Each rigid body has a configuration space of its own SE3. So we have SE3 n times. So SE3 multiplied by SE3 multiplied by SE3 n times. This is the whole configuration space. And this is the unconstrained configuration space. This means that how many bodies do we have? We have n. So we have in total SE3, which is multiplied by n. So this is the configuration space. The dimension of the free configuration space is 6 multiplied by n. Okay, so we have n rigid bodies, and each one of them has 6 degrees of freedom, right? 3 rotations and 3 translations, and then we get this big space 6n. However, we have joints. Each joint, depending on the type of it, constrains some directions. If it's a prismatic joint, then it prevents you from doing any 3 rotations, and then 2 of the translations, they are prevented, and only 1 of them is left. If you have a revolute joint, then you have 3. The bodies are no longer allowed to translate with respect to each other, and they're only allowed to rotate in 1 direction, but not 2. So, and whenever we have a joint, it's always constraining 5 degrees of freedom, and we only have 1 left. So in the end, if you take into account the constrained or reduced space, you're going to find that we have S1 and R times, and we have R and P times. So NP is the number of prismatic joints. We have R and R and R. Each prismatic joint can move in R, while each revolute joint can have S1 configuration. So can move around the circle. So the theta, what we call the theta. And all of them, the combination of all of these angles and all of these displacements for the joints in the end make up the configuration space, the constrained configuration space or the reduced configuration space. Each one of these 1 degree of freedom joint had a joint configuration and a joint velocity. We usually called it theta. We're going to be calling it here Q. So Qi for the ith joint can be in S1 or in R, depending whether it's a revolute joint or a prismatic joint. Q dot is always in R. Okay, so the tangent space of S1 is R, and the tangent space of R is R. So usually we always have that the velocities, angular velocities or the linear velocities of the prismatic joint are always in R. And then using the Q, we can use the exponential map to represent it as a pose. In the end, we have, this is a full, okay, pose. It's a full H matrix, but in the end, it's only a parameter of one variable, only variable of the Q. So you can think of this as a map that takes one number, okay, so one variable Q, and gives you in the end an element of SE3. Clear? And this, the corresponding map at the velocities level. So we know how to relate the velocity. So sorry, the generalized velocity or the twist to the pose of the two bodies to the rate of change of this Q variable, so the Q dot, and it's given by the screw axis. So this was also a map from 1 to 6. So this is a map from 1 dimensions to 6 dimensions, and this is a map from 1 dimensions to also 6 dimensions, but it's a map on a manifold. Okay, this is a map from R1 to R6, and precisely the screw axis is actually an S6 by 1, right? So you multiply by one number, which is the Q dot, and you get 6 numbers, which are the twist. Okay, and these should be familiar, okay, to you. We had a recursive way of writing the equations of motion because each twist, okay, the ith twist with respect to the S frame, with respect to the fixed frame, the stationary frame, can be expressed in terms of the twist of the link before, so the I-1 link, and in between there was the Q dot, which is the relative angle, so the relative angular velocity between both, or the relative joint velocity. And then we had that the V dot is given by the time derivative of this equation, okay? And we had that this is nothing else than the dynamics. So the generalized inertia multiplied by the V dot. This was the gyroscopic terms. This was the reaction wrenches. And these were the reaction wrenches from the next link. Okay, so you see we have this recursion here. And in the end, the torques are related to the reaction wrenches simply by the S transpose. What we did starting from here, just as a remark, that for the I equal 1 link, when we calculate, for example, its twist, then V of 1 with respect to S expressed in 1 was equal to the adjoint of V with respect of 0 with respect to S expressed in 0. What is the twist of 0 with respect to S expressed in 0? Should be in the end 0, 6 zeros, right? Because the 0 frame is the S frame. So the 0 frame is the S frame, so there is no relative twist between them. They are both the same frame, they are not moving. And this simplified things a lot. So, and you can imagine that this will not be the case when we talk about floating base. This is the only thing that will change. It's only this part that will make things change a lot, as you're going to be seeing in the end. Afterwards, what we did is that we combined all of the twists together. We took all of the V1 with respect to S expressed in 1 up to Vn with respect to S expressed in n. We combined all of the twists together in a big V, okay, variable that has a dimension of 6n. And we took all of the wrenches, combined them in 6n star. We took all of the Q dots in what we call the Q dot, which is in Rn, and all of the torques into Rn star. And then we wrote the same equations. These are exactly the same equations, but written in a compact form, okay, introducing all of these big matrices. You can go back and check them. But in the end, we reach something that looks like this. Rings the bell? Okay. Just here just to highlight something that you should have, like when you were studying this, you should have noted, but in case not, all of these twists and wrenches, they're actually the unconstrained case. So they're describing how each one of these bodies, okay, should not move separately from the other. So they are all constraints. So all of these are the twist of each body, and these are all of the reaction wrenches that constrain all of these bodies to be near each other. And all of these variables are with respect to the joints, and the joints are actually all of the directions that you're allowed to move. So you can think of this as the n directions or the n variables that describe the constrained dynamics or the reduced dynamics, and these are all of the 6n variables that describe the unconstrained variables. This is very similar to when we had the configuration space that was free, unconstrained to be 6n of dimension, and we had the constrained case to be n. So this is very much in line with it. Before we move on, we looked at this pair L of Q multiplied by S. So this big matrix L and this matrix S, they appear a lot. So they appear here and they appear here. And when we multiply, and its transpose will also appear here. And this was a very important like map that maps the Q dots to the V. And here it maps the torques to the yeah, to this side, to whatever inertia, like inertial force wrenches that we're going to have. And this is precisely the geometric Jacobian. So this is a big J matrix, and this was how scary it looked like. But in the end, we look at it row by, or like 6 rows by 6 rows, and we can combine them into all of these 6 by n matrices. So this is 6 by n, 6 by n, 6 by n, and we have them n times. Okay, so, and each one of these was the corresponding body Jacobian of each link. Okay, and we talked about the geometric Jacobian. I think it was in lecture 12 or something. Okay, so early on. And we just wrote the J in terms of this part, and you see it becomes actually very easy to look at this equation, because here I have V is equal to J multiplied by Q dot. Makes sense because J is the map from Q dot to the twists. V dot is the differentiation of this equation. So this is J multiplied by Q double dot. What do you think of this term? Exactly, it's the J dot multiplied by the Q dot. So all of this term, actually, if you remove the V and put it here, the J multiplied by Q dot, in the end, we're going to be left with something here that's nothing else than the J dot. Okay, so all of this that will be here is nothing else than the J dot. Okay, so this is just a closed form solution of the J dot. We don't need any numerical techniques to resolve this. And then we took all of these equations. You find that I have the wrench in terms of the twist. I have the the torque in terms of the wrench in terms of V dot and V, and the V dot in terms of Q double dot and Q dot and Q, and the V in terms of the Q dot. Okay, so and we can just plug in all of these equations into each other, and we can reduce them to this form: the M of Q, Q double dot, plus the C of Q, Q dot multiplied by Q dot is equal to all of the torques that are actuating this robot. The M of Q is given by all of these expressions. Here I wrote them in terms of the J. You see how compact it becomes. And here is the C matrix. This is all a repetition of what you should know. And then we added external wrenches or the gravity whenever needed. So we added the gravity torques. We showed you a couple of ways to do that. And then we have here also some interaction wrenches at the end effector. And you see the Jacobian again appears here, but this is only one of these Jacobians. This is only the Jacobian of the last link of the end effector. And this is the wrench applied at the end effector. This is a Jacobian transpose. This is the Q dot mapped by the end effector Jacobian to the end effector twist. Okay. Easy? Okay. Hopefully going from here to a floating base will not be that difficult, just with this procedure. We're going to be doing exactly the same procedure, but only one thing will change. What is it? To go back here. Which is the only thing that will change here? Only VI with respect to S expressed in I. This expression will be V0. Let's take this one actually. So this is VI with respect to S expressed in I. For the case I equal 1, we're going to have here V1 with respect to S expressed in 1 is equal to the adjoint from 0 to 1 multiplied by the twist from 0 to S in 0. 0 to S in 0 here in a fixed base is 0. So all of this term disappears. Also all of this term disappears. Also all of this term disappears when we have a fixed base. Only for the case I equal 1. So all of this disappears. And we're only left with these two terms. If we have here a floating base, then V0 with respect to S expressed in 0 will no longer be 0, will no longer be a 0 vector. Why is that? Because the 0 frame will be the base. Okay, so the 0 frame when we have a floating base will be a base, will be something that is moving already. So the only thing will change here is that when we talk about 1 with respect to S expressed in 1, we're going to have here the twist of B, which is the 0 frame, B with respect to S expressed in B, and everything else will move on. So this is the first thing that will change. And of course, these two terms will have an effect, and they will keep on propagating throughout the whole equation, because we do this recursively for all of the links. And this is exactly the term that will have the coupling between the base effects and the manipulator effects. The question is, we only change this part. How much do you think the remaining will change? So all of the stuff that were of all of the links with respect to each other, do you think they will change a lot? Or change at all? Not at all, exactly. they will be exactly the same. And this is hopefully what I'm going to be showing you on the board right now. Okay, so that's it for respect to the recap. Everything we're going to be doing now on the board will be just taking these same equations, just expanding them only with 6 numbers, which is with respect to the base, and trying to show how easy, how to reduce it again. There's just also another thing that we need to take into account. The twist of the base with respect to S. So the relative twist of the base with respect to S. What's the dimension of it? So the body frame S, the body frame B with respect to the stationary frame S. How many ways can it move? How many degrees of freedom does it have? 6. If you say 6, you're only considering one type of floating base manipulators. Something that's that's really floating, okay? That's really not at all, it's not moving, it's floating in air. It's the same term that we use as floating in English. But floating base manipulators can model a more wider class of systems. If you have something that's moving on the ground, okay? Assume something that you have, maybe it has like this thing. Let's say that I put a manipulator on it, and I put it on the table, and I start to move it. Is this floating base or not? Yes, it is also a floating base, but it's constrained. Exactly. So it's like this base is attached to the stationary frame with a joint, right? What is this type of joint? It's a planar joint. It's not a fixed joint. This is what the type of what we call a planar joint. What is a planar joint? It's a joint that allows you to move in X direction, okay, or right and left, forward and backward, and it can rotate around the third axis. What about this rotation? Not allowed. What about this rotation? Not allowed. What about moving up and down? It's not allowed. So how many degrees of freedom does this planar joint have? It has 3. It has 3 directions you're not allowed to move in, and 3 you can move in. Okay. So to be more general, we're going to be assuming that the base can move with respect to the B frame with respect to the S frame can have B dimension. Okay, so the twist of B with respect to S can have B dimensions, just to make it a little bit interesting. The special case of this is that B is equal to 6, and what does that represent? Something that can fly or something that's in water and so on. Okay, just to have the equations general. Now yes. I'm gonna write it down. I'm gonna write it down. This is just an introduction. I'm gonna be writing down. Planar should have 3. Exactly. You have 6 degrees of freedom in general between B and S, 3 rotations and 3 translations. The planar joint is allowing 1 rotation and 2 translations. So this rotation, this translation, and this translation. Okay. Another example of something that that has 3 degrees of freedom is a spherical joint. Okay, a ball joint or a spherical joint has 3 degrees of freedom. It's not allowed at all to have any translations, but it allows 3 rotations. And it will be also something we can also model it here. But this type of road it's very exotic. We don't call something that has a spherical joint. We don't call it a floating base. Okay. The reason why this is important, because if you have a robot with wheels on the ground, and these wheels are omnidirectional. If you know what that means, if you know it. If not, I'm not going to describe it. So it has omnidirectional wheels. This means that you can model it as simply a planar joint. You don't need to really look at all of the dynamics of the wheels. You just consider this just a planar joint. This is why this is interesting. Okay. Also, if you have a robot with tracks, no, tracks not. So tracks you cannot do that. So tracks you're going to have constraints. If you have normal wheels like in a car, so with steering mechanism, this is where you have constraints. If you have legs, these are all with constraints and so on. Okay. Yes. No, that's off topic. I only mentioned it to say it's off topic. No, let's not waste time in it. Just let me finish this part, and if we can discuss it in the end. So let's go to the whiteboard. So the first thing we're going to be doing is trying to describe this generalized joint between the B frame and the S frame. So we want to describe HB with respect to S and VB with respect to S expressed in B in a generalized way. Okay. So if we say that HB, so HB with respect to S, it lives in not SE3. Because if we say it lives in SE3, what does that mean? It has 6 degrees of freedom as a joint, and it can do anything. So they're not attached at all. If we want to look at this more general case, then we're going to be saying that this lives in some sort of sub-manifold, or actually it will be a Lie subgroup of SE3, and we're going to be calling it curly HB. Okay. The dimensions of this guy is equal to 6, while the dimensions of this guy will be, we're going to be calling it B. Okay. Yeah. In a submanifold of it. A submanifold, or this is a Lie subgroup of it, which means that this is a manifold, this is a group, and it's also both, and it's a set, and so on. Okay. So this is a subset of it, but it's also a submanifold, and it's also a subgroup. So in the end, we call this a Lie subgroup of it. Okay. It has the same operations as this. So this is not like it has new operations. It's exactly the same operations. But whenever we start here, we always live there. Okay. Another example. So if you have this planar joint, whenever it starts and it moves on the ground, it never goes up. Okay. And it never has any rotation. It's always living, okay, in this space. So, and it's a subset of SE3. So this is the configuration of the base with respect to the S frame. Yes.
And the H is an element of this sub-Lie group or Lie subgroup. Then isn't
No.
element of SE3?
Kenson? Yeah, this one. Thank you. Yes, sorry.
Since it's a subset, and this is an element of it, then shouldn't this also be an element of SE3?
It's always an element of SE3, yes. But we're saying that there are some directions that so an element, this one, okay, that lives in here, will not be the same as any SE3 element, right? So SE3 elements, for example, can have a height, but this base can never have any height. So this is what a submanifold means, okay? We're just restricting it. Absolutely, and this is why we have this equality, you see? We have it's a subset, or it's a subset and equal SE3 in general, okay? So this is just the general formulation. And the twist, let's put this up. And then, let me see. Yeah, okay, let's keep it like this. And then we have that the twist of B with respect to S expressed in B will be given by some map. We're going to be calling it iota, okay? And it eats a small v of the base. This map, iota, takes you from RB, which is something that lives in the tangent space here, to R6, which is this twist. Okay? And بالمثال يتضح المقال. So with an example, inshallah, everything will be clear. So let's take that with this formulation. What did we do earlier when we had a 1 degree freedom joint? Just to give you an example. So when we had a 1 degree freedom joint, okay, maybe just to be 100% precise, let me add. Okay, no, let's not add anything. Okay. So when we said that H of frame I with respect to frame J as a function of theta is given by the exponential map you all know about, okay? And this is in, where did this live? Did it live in SE3? Did this live in SE3? No, it lives actually in something that's smaller than SE3. Okay? Because this was only 1 degree of freedom, right? So it wasn't any relative pose that was allowed. It was only a particular set. When we have the exponential map, okay, we constrain this set. What was the dimension of HB in this case? 1. And the dimension of SE3 is 6, okay? So you see that's the first example. What about the VI with respect to J expressed in I? And here J is I minus 1, right? So assuming that we're connecting frame I, so frame I is one link, frame J is the parent, child and the parent, okay? For simplicity. So this was equal to some map that's multiplied by theta dot, you remember? What was this map? No, it was the screw of I with respect to J expressed in I. So you see this was something that lived in R1 because we had 1 degree of freedom joint. This was something that lived in R6. What about this was a map from 1 to 6? This was exactly the iota that's in this example. And the B here in this example is equal to 1 because we have a 1 degree of freedom joint. Okay. Theta dot. The first time you see this? The Jacobian relates it to all of the thetas. Here, this is only theta I. And inside of the Jacobian, we had S and the S and all of the S's plus each other and so on. If we go back to lecture 12, we're going to find that inside of the Jacobian was S, all of the S's plus each other and transformed with some adjoints and so on. So in the end, the Jacobian is nothing else than S's being next to each other. Okay? So this is the map here. This is an example of the 1 degree freedom joint. What about the small v? What is the small v that we're talking about? It's the v dot, the theta dot, exactly. So this v is nothing else than the theta I dot. Okay. Another example. Let's look at the planar joint. Let's first look at the 6 degree of freedom floating joint. So HB with respect to S lives where? In HB, which is nothing else than SE3. The dimension of this is 6, and the dimension of that is 6. So B here is equal to 6. What about the twist? VB with respect to S is given as the definition of something that maps some velocity that describes a generalized velocity of this joint. What is the V here? When we're talking about something that moves everywhere, can we talk about 1 theta dot, 2 theta dot, 3? 6, it's a twist, exactly. No, it's a twist. Here, this is nothing else than, this is our identity matrix multiplied by this guy. And you see that this is a map that's mapping you from R6 to R6. This is, of course, a trivial case, but just show you that this is a general way of describing a joint. So when you say that you have a joint that's connecting the base to the stationary frame, and it's a map from B to 6, when the case B is equal to 6, we just have an identity map. And we don't make a differentiation. We don't distinguish between this V and this twist. They are both the same thing.
One time theta dot, one time
Yeah. It is something in RB that describes all of the ways your joint can move, that allows you to move. So if you have a 1 degree freedom joint, you're allowed only to move in one way, and you have only one velocity, theta dot. If you have
6-degree freedom joint, you're allowed to move in 6 ways. What is this way? What is this variable that we use to describe the 6 ways that we can move in space? It's a twist. And here we're just mapping it to the same. We don't make a distinction. This is just a trivial case. The interesting one is the third one, which is when you have a planar joint. So when we have a planar joint, HB, so the H of B with respect to S is given by something that looks like this. It has cosine theta minus sine theta, cosine theta, sine theta, sine theta, cosine theta. We have 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, psi x, psi y, and 0. This lives in SE3, but it's actually living in a subset of or a submanifold of SE3. So it lives in this guy, and this is a submanifold in SE3. Okay. So, sorry, what's wrong? It is a rotation around Z. So this planar joint. So let's assume that this is the frame I chose. This is X, this is Y, and this is Z. So I put it like this. So you see I can move in X. I have an X displacement, a Y displacement, and I have a rotation around Z with some angle theta. And this is how the H will always look like. I'm not allowed to have any displacement in Z. I'm not allowed to have any rotations around X and Y. And this is why the rotation matrix in the end becomes very simple as this. It becomes only equivalent to one angle theta. And this is exactly what you do always in 2D when you have a mobile robot on the ground. You always say that I have 3 variables that describe the configuration, X and Y and angle theta. You put them in a H matrix like this, and you get something that lives in SE3. But it's not anything that's left. So SE3 has 6 dimensions. What about the dimensions here? B is equal to 3, exactly. So now I want something that will map V that lives in R3 to something that will map it to the twist that lives in R6. And this map, we're going to be calling it iota. Without a dot.
Wouldn't be the Jacobian in the case of 1 degree of freedom? Putting the F and theta dot.
No. Okay, so what do you think the variable the V is? 3 variables. You need 3 variables to describe the velocity, right? I'm going to be choosing one of them to be equal to omega around the Z, and velocity in the X, and velocity in the Y. Okay? And I'm going to map them by this map. So I'm going to multiply this, not from the right, from the left. This is just, okay. So this should be here. And I should multiply by this guy. This is a map that would eat something in R3 and gives you something in R6. And in the end, the twist will be equal to 0, 0, omega in Z, V in X, V in Y, and 0. Okay? Clear? So you see that, okay, so we're going to be dealing a lot with this is the generalized velocity of the base. Iota is the map that will transform this generalized velocity into a twist. And we're still dealing with homogeneous transformation to describe the relative transformation between the base and the stationary frame. And they're given by this expression. And by the way, we still have the same equation that H dot, so HBS dot is equal to HBS, and then V tilde B, yes. This is always valid, okay? Even for a submanifold, okay? Easy? Yes. The symbol, iota. RB. We're gonna call it RB. So the number of the dimension of the base movements. Exactly. To the relative twist between the base and the stationary frame in general, which is always in R6. Okay. Yes.
The 3 degrees of freedom we did, like, I think for the 1 degree, we could take a 6 by 1 vector.
Yeah.
And do the same, which is actually the S, right?
Which is actually the S.
Why the S here?
Exactly the S. Yes.
Okay. In some papers I saw they were writing some SE23, as if they're joining some velocities together with the position and orientation.
SE2.
Like as if they join the position.
It's so all of this stuff. So okay, so properly speaking, this guy in this example is actually what's defined as SE2. If you ever see SE2, it's this guy. It's this space here. Okay. So SE2 is a submanifold of SE3. SO3 is also a submanifold of SE3, right? If I have something, if I have a H matrix that always has 0 for translation, I'm only left with the rotation. So it's equivalent to SO3. Okay. And the dimension of SO3 is 3. The dimension of SE3 is 6. So you see this is already a submanifold. Okay. Is that your question? SE2, 3. There's something else. I think this is something related to estimation or something like that. Something there. It doesn't appear here, this space. So with this equation, so with this just introduction of this relative base, the relative movement of the base, we now need to understand if I have a floating base. And when I say the floating base, have these 2 examples in mind. So this is a cube with a 2-link manipulator on it. So this is the S frame, and we have here the B frame. So this is an example. And another example is you have let's see. And this is another manipulator. Okay. So you see here the base movement. So again, the base is also, this is the base, this is the S frame. And this base can have, so B here is an example of 3, because the base is a planar joint, while B here is equal to 6. Okay, it's a really floating, it's not attached at all to the S frame. But we still call it a joint, we still call it a floating joint. By the way, this is also the same algorithmically. So this is the same also numerically how it's implemented. For example, in the robotics system toolbox in MATLAB, when you want to simulate something like this, you need to add the floating joint between the base and the stationary frame. So what is the configuration space here? So the configuration space, if we have the unconstrained case, how many degrees of freedom do we have? So Q free is equal to what? Nope. Q free is SEN multiplied by how many? Sorry, SE3, sorry. Nope, multiplied by N plus 1. Okay. We have N plus 1 links. Whenever we talk about a floating base manipulator, if you say I have an N link manipulator, you're assuming that you have N links and you have an extra one, which is the base that's moving. So I have an N plus 1, okay, multiplied by 6. So in the end, the dimension of this guy is equal to 6 N plus 1. So I have extra 6 because I have a whole base that can do anything. But this is the unconstrained case. Usually I'm going to have a constrained version or reduced version of it because of all of the joints. So the reduced case, which is the Q, will be equal to, I'm going to have something for the base alone. I'm going to be calling it, so this curly HB that we had, so the one that we had here. So this curly HB, that's a manifold of SE3. And I have the, no, not SE3. I have for the manipulator, okay? We're going to be calling the manipulator 1 QM. So QM, if I have n revolute joints, is going to be the n torus. If I have n prismatic joints, I'm going to have just Rn. If I have a combination of both, you can have a combination. But in the end, the configuration space of the manipulator alone is QM. The configuration space of the base alone is HB, and then I have the combination of both, okay? This is not the product space of it, okay? This has a very, very special geometric structure. This is something called the principal fiber bond, okay? So if you ever see something like this called the principal fiber bundle, okay, this has the shape of it, okay? But that's off topic. So this is the, one second. So this is the reduced space. What about the dimension of it? So the dimension of Q is equal to the dimension of HB plus the dimension of the QM. And this has a dimension of B, and this has a dimension of M. So in the end, the joints that will be added, I have n joints that are in the manipulator, and I have one extra joint that will describe how the base is moving with respect to the S frame. And this joint will reduce the base movement from 6 to B. And in the end, if B is 6, then we did nothing. Right? This is just a generalization. There's a question.
There is a change from there.
Sorry?
The QM, then dimension QM.
Yeah, so okay, yeah. This is just the Q of the manipulator. I'm going to be using here M for the manipulator, and this for the base. There will be a lot of symbols here. It's hard to make it clean. No, this is the Q of the manipulator. M is for manipulator, not for the n dimension. So I have an n-dimensional manipulator, and the M is what's used here, or manipulator. I don't want to write it all down. And this is base. Okay? The dimension of the H of base is B. Dimension of the Q manipulator is N. There was a question? N is the number of links, excluding the base. So the base is an additional, okay, link or rigid body. Okay. So far, so good? Sorry? Sorry?
The movement will change depending on the type of joints and it has, right?
Yes, but everything we're doing will not change. Because in the end, we use the exponential map. And the exponential map, okay, you have it generally. We write it in terms of the S. The S itself changes if you have a revolute joint or a prismatic joint. But all of the expressions are exactly the same. Just for simplicity, throughout the course, we've been only doing revolute joints, just for simplicity. But prismatic joints would work exactly the same. Now, the key is writing the relative twist between any frame I with respect to S expressed in I. The key is to write it as some sort of Jacobian matrix I with respect to S expressed in I. It will be a function of Q. Okay. So we have two variables here. The Q is defining the configuration of the manifold. It's exactly the same as we had earlier, okay, for a fixed base manipulator. So when I say Q, I mean Q1 up to Qn. Okay. So this is Q1 up to Qn. Okay, and it lives in this manifold. And I have the base, which is in the end H, so HB with respect to S. HB with respect to S that lives in this space. And I don't parameterize it. And this is very important. Okay. This is really the first step that you do in any modeling, that you say, how many degrees of freedom does the base have? In this case, it has B degrees of freedom. So instead of writing it like this, let's writing as something in RB. So let's introduce something maybe like the Q of the base in RB. And this is completely what? Not geometric. So whenever you find something like this as a starting point that says I have QB, completely not geometric. Because they're assuming here that I can represent the base movement by 6 numbers. And you know that's not possible. Okay? It's definitely not possible. For a planar joint, for a floating joint, okay, we cannot do that. So this is the key that we want to multiply this by a combination of the V and the Q dot.
That's why you said it's not possible to parameterize it by six parameters, 6 values.
Globally, yes, it's not possible. Locally, yes, you can do that. Locally, but not globally. Okay?
No.
If you don't understand, just keep it on the back of your, or write it down, and maybe hopefully in several years you can understand. Okay? So this is just what the Jacobian will do. It will map the V and the Q dot to the twist. Okay? This map, okay, for each body will have something that looks like this. It will be, okay, instead of writing it down, okay, generally, because now to be, because we're running out of time. So what when we combine the V1 with respect to S, V2 with respect to S, up to Vn with respect to S. And on top of that, don't forget that we also have the V of the base with respect to S. Okay. From here to here, we had that before, right? When we had a fixed base manipulator, we had from 1 to n. We had n links. So we had all of this. This is just the extra step. And we wrote this as a big Jacobian matrix multiplied by Q dot, right? But here the base is also moving. And the base has a velocity that's given by this small v that has a dimension of b. Sorry, small v that has a dimension of b. So this is a b plus n vector. You agree? So b dimensions, n dimensions. This is a 6n plus 1 vector, because this is 6, 6, 6, 6, 6, and so on. So I have 6 of these multiplied by n, and I have 1 extra 6, which is the base. So what's the dimension of the Jacobian? It is something that will eat b plus n to 6n plus 6 multiplied by n plus 1. Yes. The n, not necessarily. No, it can be more than that. We don't constrain that. Okay. And depending on the number of n, we can classify the robots. You can talk about redundant manipulators or non-redundant manipulators, depending on how the n, okay, is depending on the number of n. If you have a fixed base manipulator, the minimum number of n that you need to have a full actuation on the n effector, you need 6. And this is why when you have a 6-link manipulator or more, we call this to be a universal robot. It can apply a wrench in 6 dimensions. If you have less than that, then there are some directions you can never touch. You can never actuate or go there. If I'm talking about a fixed base manipulator. When you have a floating base manipulator, again, it depends on how the base is movement, and it depends also on what type of application that you want to have. It gets more complicated than just 6. Okay. Yes.
You mentioned 6n plus 1.
6n, okay, 6 multiply n plus 1.
6n.
Yes.
But then that means we're assuming the full case of a fully floating manipulator.
No, the twist is always 6 dimensions. No matter what the base is doing, you always have a 6-dimensional base. That's the relative twist. No, the relative twist is always 6 dimension in terms of numbers. You always have 6 numbers. How many of these are zeros and how many of these are changing depend on the V. Then this is why the map iota that we introduced, this one, always maps this RB vector to the R6 twist. Okay.
So what's the difference? I'm really not understanding the difference between the small v and the Q dot.
Base manipulator. base motion, manipulator joints motion. So if the base is fixed, it's not moving, okay, and the manipulator is doing stuff, these are zero and these are changing. If the base is moving and the manipulator is locked, these are zero and this is moving.
Here, the Jacobian post here, this is supposed to be a function of Q or Q dot.
It's a function of Q. The Jacobian is always a function of Q. When I write it down, you're going to be seeing why. Let me expand this, okay? So this will be a scary matrix, but again, you know where it comes from. Actually, most of it you already saw before, and I'm going to show you why. Where. So this is a geometric Jacobian, yes. BN, yes. Thank you very much. Okay. Okay. It's ugly, but you've seen most of it before. All of this part is exactly the same Jacobian for a manipulator before. Exactly the same. We added here zeros on the top, and this is the only thing that changes here, you see? All of this is due to the effect of the base. And you see the only thing that we have here is the iota. Iota, but for the first one, and then we have iota from B to 1, and iota from B to 2, iota from B to N. The transformation from B to 1, let's take this example. The transformation from B to 1 is the inverse of 1 to B. How is this transformation from 1 to B? What is it related by? So H, if I want to write 1 with respect to B, how do I calculate it? Remember that the B here in this example is nothing else than the 0. So 1 with respect to the 0 frame is a function of theta 1, or in this example, Q1. And you know that how do we calculate it? Multiply by 0 exponential blah, 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 blah. Okay. So you see H1 with respect to 0 or H0 with respect to 1, or here B with respect to 1 is a function of theta or the Q. And all of these are function of Q. You see, all of these transformations are a function of Q. So in the end, everything in here is constants, iota, and all of these S's are constants. And we have the adjoint that is only a function of Q. So in the end, this whole Jacobian is a function of Q. And this is something very, very important. You see, even though the base is moving, this is very strong. Even though the base is moving and doing all sorts of stuff, its motion doesn't affect the Jacobian at all. We don't see the V, this V, inside of here, inside of the Jacobian. That's all. That's one thing. What's even better than that, the configuration, which is HB with respect to S, also doesn't appear here at all. So this Jacobian is only a function of the Q of the manipulator, not the Q and the H of the base. And what you see here is that we can rewrite this whole thing as something, okay. Let me see. Okay, so this is the whole, so this whole thing is the Jacobian. So this whole thing now is the Jacobian as a function of Q. It's of the base, it has a base part, it has a manipulator part, this is zeros, and this is the coupling that will cause the base and the manipulator to be related to each other. Okay. And again, there are more stuff that we can move on, but this is the key thing. If you really understand this, the rest is just okay, a bit of math. But what I want to show you in the end, this is the end result without showing you how to reach there, just to show you okay, the benefit of this. And again, there are stuff that if you're interested and you want to use that, you can read about it. But again, the bottom line is that the Jacobian, we can write it as something that looks like this. I can have iota on the top. I can have here a bunch of zeros. I can have here the Jacobian of the manipulator as a function of Q. And I can have here something that is an L matrix similar to the L that we had, that couples between the manipulator and the base. And this is also a function of Q multiplied by the iota. Okay. So you see this part here is this purple. All of these zeros are the zero, the iota is the top left, and all of what's in here is iota multiplied by a bunch of matrices. We're going to be calling all of them M. Looks like this. But the nice thing is because of this this Jacobian, if you go back and try to do the same process that we did for taking the twists, taking the torques and the wrenches and the V's and so on and the V dots and plugging all of them together, you can reach in the end an equation that looks like this. M of Q V dot Q double dot plus C of Q, V, and Q dot multiplied by V and Q dot. And then we have not only torques at the joints, we're also allowed to have actuation of the base. If we have any forces on the base, we're going to be calling this a small w that's like the dual variable of the small v. So if the v has an r is an rb, if I can move around the z, for example, in a planar joint, if I can move around the if I can rotate around the z and move in the x and the y, this will be the force in the x and the y and the torque around the z that will make me move. This just as an example. But in the end, we get an equation like this. What's even better than that is the way how the M of how the mass matrix will look like. We can decompose it into something that looks like this. Something that's related to the base alone, and it's a function of Q. Something that relates the manipulator alone, and it's exactly the same mass matrix that we had for the manipulator. And then we just have a coupling term that's only one of them because the mass matrix in the end should be symmetric. So this is BM transpose. We have something that looks like this. How do we calculate this one? Okay. So in the end, where does this M come from? Okay. So this M in the end is nothing else than the J transpose of Q multiplied by all of the inertia tensors multiplied by J of Q. And you see the I itself, it had the inertia of the first of the base and also of the N links. The J here, I can decompose it like that. And the J transpose, it's just the transpose of this. And you see it's trivial to find what are all of these expressions here. And I can calculate them to be in a closed form solution. You can do exactly the same for the C. You can get a closed form solution for all of the inertias, the adjoint, and so on. Exactly in the same way that we did for a fixed base manipulator.
You can generalize in the chip.
The I here is generalized inertias. So this will have the inertia of the base in the base frame, the inertia of 1 in the 1 frame up to n in the n frame. We just added everything by 6. We just add 1 row in all of the expression that we have. 1 sec. So this is just the end result, and I'm gonna stop here. Okay, but this is what, again, there's a lot of stuff that I hid. Okay, for your own sake. Okay, so, but this is precisely what I want you to see, because this is usually the starting point for any paper on floating base manipulators. This is just the starting point. They assume you know how to calculate it. You know, assume how do you get it. This is how you get it in a very easy way, knowing, okay, all of the different stuff, okay, all of the different parameters, all of the inertias and all the transformations in between. This is exactly what the URDF file that you build does for you, okay, because in the end, you tell it all of the inertias, you tell it all of the joint transformation, and it will calculate this. It will calculate everything you need inside. The simulation of this is exactly what Gazebo does, okay, or PeliaSim or NVIDIA or whatever. They just have smart ways of transforming this into something on the computer. But in the end, you need to know this if you want to do control, if you want to do model-based control, if you want to design a controller for these guys, such that the V, which is the base movement, and also the Q dot, which is the joint velocities, if you want them to follow some desired trajectory or to stabilize it or and so on, or to do impedance control, blah, 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 this will be your starting point. Okay, so what I wanted to emphasize here is that if I chose this not to be a V, but to be some Q base dot. So if I chose instead of V, I chose Q B dot to be in R B. This is usually not the geometric approach. Okay. So the bottom line is you all know for now that a twist is not the time derivative of anything. You all agree? So it's related to the time derivative of the H by H dot is equal to H multiplied by the twist tilde. Right? So this map that has the geometric structure underlying it. And the same also here. I cannot write that the V is the Q dot of something or the dot of some variable, but this is usually the starting point in many papers that do it in a non-geometric way. So if you find this to be written as a big Q double dot, another Q, not this one, a Q total double dot, and this is a Q total dot, you know immediately this is not geometric. If you find this separation, this is geometric. Okay. Let me stop here. So this is the end of the course, yes, end of the recording. So if you have any questions, I can take them offline. But so from now you're on your own. Okay. سبحانك اللهم وبحمدك نشهد ان لا اله الا انت نستغفرك ونتوب اليك.